Hey everyone! So today we are in chapter 16. We are talking about acids and bases. Acids and bases are things that you encounter in your everyday life. And even though acids are known as the strong type of solution that can eat through anything, bases are actually just as dangerous as well. Some acids that you deal with in your everyday life are ones like lemon juice, vinegar, which is acetic acid, and then those car batteries that you have are filled with sulfuric acid. Bases that you deal with are things like soap, drain cleaner, any type of cleaning detergent is a type of base. So today what we're going to focus on is we're going to focus on how to identify an acid or a base, how to tell if an acid or base is strong, whether by knowing the strong acids and bases, and through the K constant, which tells us how strong an acid or base is. And we'll get to that in a little bit. But first, let's talk about acids and bases. So when we used to think of acids and bases, we said it's anything that starts with an H, right? So HCl, HBr, HNO3, those are all acids because they begin with H. And we said that anything that's a base is something that ends in OH, like sodium hydroxide, potassium hydroxide, and calcium hydroxide. So everything that starts with that H is an acid, and everything that ends in OH is a base. Well, this is no longer necessarily true. Okay, acids and bases can be in different kinds of formats. So what we're going to do to figure out if something is an acid or base is we're going to use the Bronsted-Lowry definition. So forget what you know about identifying acids and bases because we're going to talk about a new method, and that's the Bronsted-Lowry definition, okay? Let me get a better marker. That looks terrible. Let's talk about, that's terrible as well. Let's try this one. That's better. Bronsted-Lowry definition. Okay, so this is the advanced definition that most scientists use. An acid donates a proton. Okay, and donating a proton is usually done through the ion H+, right? And a base does the exact opposite. It accepts a proton, which again, the proton is delivered in the form of H+. Okay, so Bronsted-Lowry definition, acid donates a proton, base accepts a proton. So if we're looking at a reaction like HNO3 and H2O, and it becomes H3O plus and NO3 minus, okay? I want you to identify the acid and the base in this reaction. Let's see if we can make this a little bit darker so that you can see at home. So, again, we're identifying the acid and the base. And here's the nice thing about an acid-base reaction. Okay, we used to think that acid-base reaction produces water and a salt, but not anymore. Okay, we're forgetting all that we know about acids and bases. The acid and the base are going to only be on the left side of the reaction. So your acid and base are going to be over here. Well, what are these guys going to be? Well, your acid is going to become the conjugate base. Okay, and I'll explain this more once we get to it. And the base is going to become the conjugate acid. Okay, so pretty much whatever we're going to identify the acid and base on this side, and whatever the acid becomes, it'll be the conjugate base. It becomes the reverse, essentially. And, well, whatever the base becomes, it'll become the conjugate acid. And you'll see what I mean here in just a second. So if you're like, Mr. Dahmer, what are you talking about? I'll explain here in just a second. So again, acid becomes conjugate base becomes conjugate acid. So we're looking at this, and remember, acid and base are going to be over here. And the acid donates a proton. So what I'm going to do is I'm going to look over here and look for which compound, when it became a product, lost an H plus. Okay, so I'm looking at HNO3, and it looks like it became NO3 minus. Remember, acid donates a proton or loses a proton. Well, it went from HNO3 to NO3, so this guy must be my acid. Okay, once again, an acid donates a proton. If I look at HNO3, which is nitric acid, it changed to NO3 minus, which means it lost a proton, so this must have to be the acid. So this means this automatically has to be the base. But let's look at our definition. A base accepts a proton. If you look at H2O, it has now become H3O plus. It gained a proton, right? It went from H2O nothing to H3O plus. So it gained a proton. So that's why it's the base. And remember down here, my acid becomes my conjugate base. So my acid here became NO3. That NO3 is now my conjugate base. And now my base became H3O plus, so now that H3O plus must be the conjugate acid. Okay, so we got to get really good at identifying the acid and the base, the conjugate acid and the conjugate base in our reaction. Let's go ahead and let's do a few more examples involving these. All right, everybody, so here we have some examples where we're going to have to identify the acid, the base, conjugate acid, and conjugate base. I'm going to start with the acid, okay? The acid is the one that donates a proton. It gets rid of a proton. So if we're looking at these two guys, NH4 plus and H2O, which one donates a proton? Well, NH4 becomes NH3, right? It loses a proton, so NH4 plus must be our acid. That means water must be base, but let's just make sure bases accept protons. Looks like H2O gained a proton here, right? It went from H2O to H3O plus, so it is the base. Remember, the acid becomes the inverse, so the acid becomes the conjugate base, so that means that this acid turned into a conjugate base, and the base turns into the conjugate acid. We go to the next one, okay? We look at this, and H2O looks like it goes from H2O to OH minus, and CO32 minus goes to HCO3 minus. So remember, the acid donates a proton. Well, it looks like H2O got rid of that proton and become OH minus. And if we look at CO32 minus, it gained a proton. It went from CO32 minus to HCO3 minus, and now it is the base. So the acid becomes the conjugate base, and the base becomes the conjugate acid. Two things about these first two before I go to the third one, okay? If you notice, H3O plus is on the product side here, and OH minus is on the product side for this one. If you see H3O plus on the product side, that means that this is a acidic solution. Okay, whenever you see H3O plus on the product side, that means it's an acidic solution. If you ever see OH minus on the product side, that means it is a basic solution. Okay? We can only determine that at this point if there's a H3O plus or OH minus on the product side. As you can see, this guy does not have, let's see if I can block that glare. This guy does not have an H3O plus or OH minus on the product side. So that means that this one we can't determine if it's acidic or basic yet. One more thing before I move on to this third example. Look at water. Water acted as a base in problem 1 and an acid in problem 2. So water can act as an acid or a base. If it can act as an acid or a base, it's called amphoteric. Okay, amphoteric can act as an acid or base. Okay, lots of compounds are like that. A lot of them can donate a proton or accept a proton. So amphoteric can act as an acid or base. I know that's a little hard to see. So this last one, acid base conjugate conjugate base, we got HPO4 2 minus. We got NH3. Okay, so remember, acid donates an H+. NH3 went to NH4+, so that didn't donate a H+, it accepted one. So this is our base. And HPO4 became PO4 3-, so that means that this is our acid. Base becomes the conjugate acid, and the acid becomes the conjugate base. Right? So that is the Bronsted-Lowry definition of acids. Now let's do another example with this where I might just give you one compound and I want you to tell me if it's an acid or a base. So here's another type of problem that you might see. The first one, it says, what is the conjugate base for HClO4? So I give you this compound, it's HClO4, and I want you to give me the conjugate base. Well, the good thing to know is that what is attached to the conjugate base? Acid, right? Acid becomes the conjugate base. So if I'm looking for the conjugate base for HClO4, that must mean that HClO4 is an acid. So what we do is we look what it's asking for and we find the pair. So it asks for conjugate base. The pair that goes with the conjugate base is the acid. So we're going to treat HClO4 as an acid. And what do acids do? They donate an H+, right? So if this guy's an acid, it's going to donate an H+. Its conjugate base is going to be ClO4-. So that is our answer. Again, look at what I'm asking for, find its pair, and then go from there. So conjugate base's pair is acid. We know that HCl4 is an acid. Then we go from there. We know acids donate a proton. What is the conjugate acid for H2PO4-? Well, conjugate acid is paired with what? Base, right? To get a conjugate acid, you got to go from a base. So, what do bases like to do? They like to accept protons, right? So if this guy's going to accept a proton, or H+, it's going to become H3PO4. So that is our conjugate acid. Remember, we went conjugate acid, the pair to conjugate acid is the base. What do bases like to do? Accept protons, so now it's H3PO4. Let's go ahead now and let's talk about strong acids and weak bases and weak acids and strong bases. So I'm going to start this next section asking the question of what makes an acid or base strong? And in your head you might be saying the one that eats skin the most, right? Or the one that dissolves the most. But how does an acid get to the point where it can dissolve things so very, very well? Well, the answer to this question as to what makes a strong acid or base, it's the one that dissociates the most. The one that dissociates the most. And you might be saying, Mr. Dahmer, you just made me more confused than you did to answering the question. What does dissociate mean? It means break down into its ion. Dissociate, right? You want to dissociate yourself from those people. You want to get away from them, right? It means ionize, dissociate, dissolve, any of those things, okay? So let's look at an example of this. We have HCl, which is a strong acid. And we have HF, which is a weak acid. HF is actually more dangerous just because it's so small, and we'll talk about that some other time. So if I take HCl and I put it in a beaker, HCl dissociates a lot, which means it breaks down into its ions, like H+, Cl-, and there's tons of those. And those H+s and Cl- are ready to react with anything. HCl is actually what your stomach acid is made up of, okay? It's ready to react with anything. Those H+s, as soon as I dump them on something, whether it be your skin or the floor, they're ready to dissolve and eat up that skin because they're in ions ready to react. If I put HF in a beaker, it doesn't dissociate a whole lot, okay? A lot of it's just HF. Okay, there might be a little H+ here and a little F- there. Okay, it is an acid, right? But if I dump it on you, it's not going to hurt that much, okay? It's not going to dissolve your skin instantly, okay? This is vinegar that does that as well. Vinegar does not dissociate a whole lot. It is an acid, right? But it just doesn't dissolve your skin because it doesn't dissociate a whole lot. So a strong acid is one that breaks down into its ions or one that dissociates a whole lot, okay, which we see with HCl and HF. So what you need to know are the strong acids and the strong bases. There are 7 strong acids and 8 strong bases. And those are the ones that dissociate the most, the ones that like to break down and eat our skin. All right, but they're also good for other things, not just eating skin. They're also good for batteries and carrying out certain types of reactions to create other chemicals. So once again, let's look at our strong acids, which again, there's 7 of them, and our strong bases, which you're going to have to know these in your head. There's 8 of them, so 15 chemicals you have to memorize. The strong acids are HCl, HBr, and HI. Okay, hydrochloric acid, hydrobromic acid, and hydroiodic acid. The strong acids are HNO3, H2SO4, HClO4, and HClO3. The strongest out of all those will probably be nitric acid. Nitric acid actually dissolves your skin on contact. It is a very dangerous acid. It's also a great oxidizer, which means it creates a lot of oxygen. So you have to remember those strong acids. Our strong bases are LiOH, NaOH, KOH, RbOH, and CSOH. And then we also got calcium hydroxide, strontium hydroxide, and barium hydroxide. So these are all our strong bases as well. Those are ones that are really reactive and dissociate a whole lot. So those are our strong acids and strong bases. Okay, so you got these ones to memorize, but there's also a nice numerical way to tell if an acid is strong or a base is strong or not. And it is through the K constant. Okay, let's see what that is all about. So we will have something called Ka or Kb. Ka and Kb, this is the acid equilibrium constant. And this is the base equilibrium constant. And the only thing you have to know about these, okay, is that they are a numerical value with no units. If the K is greater than 1, it is a strong acid or base. If K is less than 1, it is a weak acid or base. So an example of a K that would show you that you have a strong acid is one that's 1 times 10 to the 7th. Has a K of 1 times 10 to the 7th. That is a lot greater than K. That is a strong acid that will eat through your skin and react with anything in sight. A weak acid would be one like 1 times 10 to the negative 7th. That is a really, really small Ka. You put that on your skin, it's not going to do anything. It might actually just taste sour like vinegar does. Right? So if I were to give you an acid rating like, let's say H3PO4. H3PO4, and there's not a whole lot going on there. I just want to say that the Ka is 1.5 times 10 to the negative 3rd. And I would say, tell me if that acid is strong or weak. Well, you would just necessarily say, well, it's H3PO4. It's not one of our strong acids. Okay, so it's definitely a weak acid, but also it's got a Ka that's a lot smaller than 1. It is not very strong at all. It is weak. All right, guys, that is our lesson. So now you should be able to identify acids and bases based on the Bronsted-Lowry definition. You should be able to list the strong acids and strong bases, and you should be able to understand the equilibrium constant, Ka and Kb, and how that represents a strong acid or a weak acid, or a strong base or a weak base. That's it. If you have any questions, let me know, and have yourselves a great day.